Okay, I think we'll go ahead and get started. I know a few more folks will be joining us shortly. Let me go ahead and open us up in prayer, and then I'll give you a sense of the things that we're going to be covering today. So, dear Heavenly Father, Lord, thank you for the chance to be working with each of the students in this course. Pray that the material will be clear, that they can get a better understanding what it means to be an engineer working in the real world, and specifically for what we're covering, thinking from the perspective of a systems engineer. Pray that you would help them with their spiritual formation, Lord, that they can get a chance to be looking back at all the wonderful things that they've been able to um, learn from Scripture. And I pray that you would help them to be applying them, and also with the theological constructs that we derive from that, how that's going to be helpful for them now and in the future. And also give them interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. Okay, well, we're going to be talking about operations today in the lecture portion. And then I'm going to be talking about the parametric diagram, which is the last part of our project piece before we start to stitch it all together. And so one of the things I just want to remind you of this, one of the textbooks that we have is the Practical Guide to SysML. And so I'm going to walk through a little bit of the information from a chapter that talks about the parametric diagram to give you some more insight. So Freudenthal and others have done a good job with what they have here capturing material in that book. So we've gone through all the different phases of a system development. Now we're in the post-development stage. And this is an interesting thing. This is where it's showtime. It's actually working. It's doing whatever it's designed to do. And so I'm going to, as I have typically been doing, we'll be referring to the James Webb Space Telescope as an example that'll include some slides just for you to be thinking about it. And I'll just keep doing that over the next few lectures that we have. So in terms of operation and supports, let's think about these types of things that happen in those things. And I'll have a couple graphics that'll show this. There's the installations. That's when it's first actually put into its operating mode. Then you have to do this maintenance. Sometimes it's called O&M, operation and maintenance. And so there's some things that have to be replaced, repaired, upgraded. And then finally, you can have an upgrading of the system that isn't just replacing a unit, but it's actually you're increasing the performance. Now, if we're thinking of something like the James Webb Space Telescope, that really would not be easy to do. But the Hubble Space Telescope, talking about two things in the same domain, that's something that was possible. They've had several servicing missions to improve its performance. So the application of system engineering principles and expertise continues to be required throughout the operational life of the system. It's a little bit different using those lessons learned. You're capturing them and then applying them. And so the operations and support phase includes installation and test. So during the early checkout in that environment where it's supposed to work, the in-service support, making sure that it stays nominal. Maybe there is some type of anomaly and maybe you switch over to a redundant unit or something like that. And then there's the implementation of major system upgrades. Maybe in terms of a space analogy, I've mentioned GPS that needs a minimum of 24 satellites to have a full constellation that you can get position, navigation, and timing worldwide. And what they do is when they have a contract to upgrade some of the satellites, and say like 4 to 8 would be awarded, and so they have a certain portion of that is upgraded, while it's still performing. So the interface integration and test can be challenging due to a mix of various organizational units. Maybe you're dealing with multiple companies. Maybe there's multiple stakeholders. I'll mention a little bit about the James Webb Space Telescope, and it's the same thing for the Hubble Space Telescope, that there's these various stakeholders that you all have to be working with. There can be a complex external interfaces and incomplete or poorly defined interfaces. Those are all things that are going to be exposed when you're actually doing operations. Well, I recently found out about something that is used both for the Hubble as well as the James Webb Space Telescope, and they have like this institute that actually operates it. And so for both of these, it's not only the US, it's Canada, it's a European Space Agency, it's a Canadian Space Agency, and some other stakeholders that form this consortium. And so having a entity like this, where all of these different components can start to give the request. And so this institute, the Space Telescope Science Institute, does the allocating of resources by the stakeholder groups. Maybe say NASA funded 60%, ESA funded 30%, Canada 10, whatever those relationships are, that would maybe give them the percentage of observation times that they can start to map out and share. And so that's where it gets into, okay, tomorrow at 6 p.m. Zulu, they will get an hour of observation time. Then there's data analysis. There's a lot of work that you get a raw image. Maybe you're doing some imaging, or you're doing some spectral analysis. Those are the two things that James Webb Space Telescope focuses on. And then there can be various integrated teams that are, say, like NASA is a primary person entity for the bus. Then you have the sensors. Maybe there's a sensor from ESA or what have you. And so then you could have various integrated teams that would be necessary to do different things. And finally, there's the telescope operation and maintenance. As I said, with Hubble, you could actually go up and service it. For the James Webb, it could be changing or upgrading the processing software that's used to communicate with it to ground, or help you to manipulate and do better analysis of what you're receiving. So maybe none of you have been to a control room for a space system or some very large, complicated system, but this just gives you an idea what it would look like. And this is they're showing on the main screen. It's maybe a little bit out of focus there, but this is 15 years that the ISS has been in operation. So with that date, it actually shows us this is 10 years ago. So now it's been 25 years that the ISS has been operational. But this is what a flight control room would look like. You have different stations that would be responsible for different parts of the system. Maybe you've seen like a launch of some NASA related mission, or SpaceX doing a launch. This is what you would see, something that would look like this, and they would have multiple displays and all kinds of communication networks that people could dial in. Not everybody would be in this room. They could be at other places around the country or around the world. So maybe that just gives a little bit of perspective of what operations could look like. So in terms of the system life cycle, now we've gone from production and deployment. Now we're in this operation and support. So all the operation and maintenance documents have been passed on. So if something happens, there's going to be a troubleshooting set of documentation that they would be leveraging. The installed operational system is actually deployed. And so this is the thing that's going on. And then we get into system operation, logistics support, and then you do upgrades. And the next slide will show it in a slightly different way that you'll get a chance to be thinking about. So what happens to the Hubble Space Telescope? Heaven forbid that one of these days it's going to have to be decommissioned. And so with its orbit, it's going to will be put into a decaying orbit and burned up, hopefully largely, if not completely, as it's going back to Earth. Well, for the James Webb Space Telescope, guess what? It's never going to be disposed that way. Eventually, there'll be a time when it's turned off in one form or another. And so there needs to be a disposal plan. And then you have to be thinking of what do you do with an obsolete system. Maybe with a James Webb, even if it's only partially functional, they'll still keep it in its limited operation until finally that goes away. Well, this also is a graphic from our textbook that shows what takes place in system operation. You can see that there's the initial installation, that there's a big surge and a lot of effort to do things from that point of view. But then you can have like you have some anomaly, and maybe you're gonna have to do a repair. All of those things are things that take place. You can have scheduled maintenance, and so say every year, every 2 years, or certain type of things that have to be serviced. You could have a system upgrade, and you can see that would be a huge expense because you still have to be doing operations, but then you're going to doing retrofit, and you'll have maybe some things that are going to be operating in parallel. And I'll have a couple of figures that'll show that. And finally, the system disposal, that's going to be a little bit of a spike to make sure that you safely dispose of this in one form or another. Before class started, one of you guys is working on a nuclear power plant, and like the San Onofre power plant between San Diego and Orange County, it's now going through that decommissioning cycle. And so you can see that there would be a spike, maybe a larger spike for that versus other types of systems. Maybe if you have an electric vehicle, the way you dispose of it. I know Elon Musk and others that would want to recycle a lot of the components. Probably the largest number of things that kind of a car would have would be batteries. And so taking those raw resources and reutilizing them would be useful. Okay, for installation and test. And so installation and test problems can be difficult to solve because installation staff have limited system knowledge. This is an unfortunate fact that the folks that were the individuals that made this, that designed it and manufactured and then passed it on to the operational team is different. And so there'd be a larger percentage of folks that are maybe technicians or folks that are just used to being out in the field. System engineers are unfortunately seldom assigned until trouble is encountered. And so you could be available on call, but you're not necessarily going to be sitting at the console in some kind of an environment like this all the time. But when something comes up, you're going to be brought up. So however, periodic operational readiness testing is necessary for the system that do not operate continuously. This can help minimize unexpected system problems. And so a missile silo, it's not going to be used all the time, but it periodically has to have that operational readiness to make sure that in a moment's notice, it's going to work. When non-disruptive installation is required, care to plan the installation procedures via a hybrid simulation or a duplicate system operating in parallel is absolutely necessary, and we'll see that in a second. So system installation, there's various things that are things that need to be thought about. The interfaces, the internal system interfaces, you have to be thinking about the system integration site. Hopefully there's not going to be any snafus with that, and plus the external system interfaces. So here's the first way that you could do a deployment. Maybe you don't have as much hardware to have a parallel system, so you can be using a simulation. And so a system of system simulation where you have an operational system and you're integrating some new capability. That would be one possibility that you could do it. And so you're doing your verification and validation to make sure that you have a good idea about that. Or another thing is you can have a duplicate system. And so maybe one is the heritage way of doing things, and you have another one that's a duplicate that now has a new system integrated into that. And you could one time, there's going to be an assigned date that says you're going to switch over. Now this would be the primary, and this other one would be a backup and decommissioned, and maybe some of those would be retrofitted to part of what would be now the new baseline. So those are ways of how you can be doing installation and dealing with some of the upgrades. In terms of in-service support, the system software must be subject to strict configuration control to prevent serious deterioration of software quality. So software is going to be important. So in this vein, built-in fault indications are very valuable for detecting internal faults, although they sometimes produce false alarms. Maybe that's a little bit better than not capturing some type of an alarm. Therefore, field engineers should be knowledgeable about built-in test devices. Remedial action to correct operational problems are difficult to implement. And so operational personnel are not the technical specialists. I already mentioned that, so that's something that needs to be considered. So there's always needs to be someone that's on call. Furthermore, troubleshooting tools are limited, and materials and processes involved in logistics to support themselves constitute a complex system. So it can be challenging, but this is where you're going to try and leverage things that have been brought in to the system to help prepare you so that these are things that you can actually be able to manage. We mentioned operational readiness testing. Every once in a while, you do a drill. That may be something that you would need to do depending on the type of system you have. And commonly encountered operational problems can include software faults and complex interfaces. There's something that goes on with that interface. So this might be something that would be a lessons learned that flows back into the next block update. Maybe we need to simplify those interfaces in what other way that can be done. Plus, there's other things that are mentioned in the textbook: field service support, scheduled maintenance, and field changes, severe operational casualties, things that fail, and also logistics support. Then in terms of the modernization, having major system upgrades, logistics cost is a large part of the system cost. And you could just see like this, that the system upgrade mushrooms all of the other items when we saw that chart that I showed a few minutes ago. Therefore, pre-planned product improvement facilitates improvement of the system during major upgrades. Advanced features are defined during system development, and advanced planning permits minimum disruption to system operation. Then we have the system upgrade life cycle. So now we're doing the system engineering V like we've done in the past, but slightly different. If it's operational, we're just doing a retrofit. So that gets into like, well, what are we doing here? How much different is this going to be? But like GPS, you have to constantly keep it operational. And so you always have to make sure there's at least 24 satellites that are up there working. So there's conceptual design, the conceptual development, there's the engineering development, there's a system test and evaluation, and the operational support. All of those are things that we've covered up to this point in this class. There's the software upgrades that need to be thought about, and there's also pre-planned product improvements. Maybe there's other things that are part of the doctrine that have been provided to you of how you're supposed to go about your operations and improvements. Then just to finish up, operational factors in system development. Possible sources of operational knowledge include operational and installation test by observing system operations within its environment. So this is one of the things that a system engineer can be working with the operators to capture that, so that can be passed on back, fed into when you're doing an upgrade or a new system. And of course, assistance from operation and maintenance personnel is invaluable to ensure that you capture as much as possible. So in terms of the sources of operational knowledge, you can, on the system readiness test, the operational modes, how effective it was in each one of those things can be helpful. And as I mentioned, the assistance from operational personnel. So it's a relatively short chapter, but it can be a hugely exciting part of what's taking place. And maybe this is where, from a system engineering point of view, maybe some of your activities kind of wane, but if something comes up as an issue, it's going to mushroom back up again. So we talked about installation, maintaining and upgrading the system. We talked about the installation and test, how we work that out. We talked about in-service support. And finally, major system upgrade when there's a need for modernization. And also we mention operational factors and systems development. Any questions on that? Okay, well, let's move on to now a couple other things. And let's see if it kicked me out of sharing. It did. Okay, let me share my screen again. So let me go through kind of typically how I've done this, but I want to make sure I spend at least part of the time going over Freudenthal's textbook to give us some information. So this is from Freudenthal's. He did this special class on SysML, and I've been leveraging these handful of charts that he has for each of these diagram types we have in SysML. And so this one is talking about parametrics. And there is a nice little introductory section in the Freudenthal's textbook that I'll show in a minute, but this will be a way to be thinking about. So parametrics, you have like equations, constraints, and stuff like that. You can do trades. And so parametric diagrams are used to express constraints, or you can be thinking of those in terms of equations between value properties. Provide support for engineering analysis, for example, performance and reliability. How does it perform if we have a 50 kilowatt hour battery, say using an example for an electronic vehicle? Or what about for a 75 kilowatt hour battery? Or an 100 kilowatt battery? So if we did twice the amount of energy that's stored in that car, but the cost is twice as much, is that still going to meet what the consumer wants? And so we can do those trades here using parametric diagrams. It facilitates the identification of critical performance properties. There's something called a constraint block that captures equations. So F equals MA is an example. And you can have expression language in various forms, either something that's more formal, and there's various type of modeling language or control language that shows that, or it can be less formal. This also facilitates interfaces with computational engines to provide the applicable analysis tools, and not just something that is done by SysML. SysML could be the conductor. Let's say there's an interface with MathWorks, MATLAB, or something like that. That would be an example of something that could take place. With our version of visual paradigms, we're not able to do that, but if we got, a larger, more enterprise version, you can. And also the version that I have with Cameo Systems Modeler, it does have that capability. Parametric diagrams represent the usage of the constraints in an analysis context. The binding of constraint parameters, thinking about those equations again, to value properties or blocks are done. So say you can see that there's going to be a connection between a block definition diagram and parametric diagrams. And I'll show that to a degree here in this discussion. Hopefully it won't confuse us as we go about doing that. So parametrics enables integration of engineering analysis with design models. Okay, so we have this model-based system engineering, this digital twin that we're trying to help us to turn it into reality. And so this is something that can be helpful. So there's this is just one example, and some of these are mimicked in Freudenthal's textbook, but this is trying to do a vehicle acceleration analysis. And so what is a gravitational force? And you can see that what is the weight of the vehicle? That would be an input. And then we have an incline. One of the things I've taught a couple of times is kinematics, doing physics courses. And so incline, you can see that you have to think of your trigonometry. And so Gravity is always going to the center of the earth, but if you're at an incline, it's going to be affecting what the gravitational force is going to be in the direction of the road because you're not on a flat surface. And so we have all of the things that we are familiar with, the powertrain. And so we're looking at the force that's there, how it is going to contribute to the total force that's available for the locomotion of the car. That translates into acceleration. There's a certain rate of acceleration that it can do. If you have like a regular gas engine, and so what is the size of that engine? If you double that, it's going to have greater acceleration. There's a larger force that can be applied. All of those things are there, and ultimately we're looking at trying to make it so that the operator can make the vehicle go at a certain speed and maintain it at that speed. There's a drag, and so the tires are hitting the road, and so where all of these things are connected. So even though this may look relatively simple, you can see that there's starting to be some complicated things that we're starting to get our head around. Okay, so this is where we see this relationship between a block definition diagram and a parametric diagram. Now, I was trying to do this in visual paradigms and getting this kind of a connector between a block and a constraint, or I should say between a block and a constraint block. I was having some challenges with that, and I'll mention that, but you can put a constraint in a parametric diagram, and it will actually show up on a block definition diagram, and I'll show you an example of this. And so this is just another example. This is just thinking in terms of an analysis context. And I'll have a slide from a different slide deck that I'll come back to that analysis context to hopefully help fill in the details for that. So here we have another one. This is we're looking at vehicle dynamics. And so there would be some kind of relationship to maybe this diagram I showed a couple of slides before with what we're trying to capture here. So for a parametric model, it depicts a network of equations that constrain the properties of blocks. The properties of the system are bound to the parameters of the analysis equation. For example, the vehicle mass is bound to the m of F equals ma. So if we can see that so this is the governing equation that we're trying to embrace with our parametric diagram. So for an example, in the figure, the properties of the vehicle are bound to the parameters of the equations used to analyze vehicle stopping distances. So if you have a mass, I'll go back to my electric vehicle, we're not thinking about how far it can go, but in terms of how fast it can stop. And so if you have twice the amount of batteries, guess what? It's going to be a lot heavier. This mass is going to be larger. And so if I'm trying to create a braking force, that force is going to have to be larger. It's going to need larger brakes. So it's just, there's various types of forces that you would have to be thinking about. Parametric models thus help identify the properties of the system that are critical to satisfying requirements. And you can start to do trades. Well, let's try it with a 50 kilowatt hour battery. Let's try it with a 100 kilowatt hour battery. And thinking about, well, what is the area that we're trying to explore in this particular context? So this is now another thing that Freudenthal has talked about. He talks about this gate operating system, and this is looking at the operational effectiveness for this gate system. And I think this is, sorry, I didn't catch this. I didn't move this back over here so it's not in your way, at least here in the room. So this is in an analysis context. And so here we're looking at these things called measures of effectiveness, an MOE. And so this isn't something I've explored in visual paradigms, so I don't, there may be a way of doing it with the version that we're using. It may not be. But these are all things that are now trying to be that we're trying to be considering for what is the operational effectiveness function. And so if we change the availability from 0.99 to 0.999, for example, that's going to impact other things that would be needed to be upgraded to make that availability happen. So that's just an example of that. The credit card processing time, it needs to be connected to the internet, and those servers have to be online. So what happens if the server goes down? That could be something that would definitely impact the time. If you have a slow internet connection, that would also be something that would affect the processing time. So those are just a couple examples. Okay, the next handful of slides that I'm going to show you are screen captures from Freudenthal's textbook. And so I'm going to be going to that textbook in a minute, but so this is just going to be just sort of a flashy kind of set of diagrams, but you'll see them in a few minutes. And you can also just be looking these up in Freudenthal in chapter 8. And so this shows you how constraints can be at various levels. And so you have the power consumption, and below that, we're here now we have like a physical law that we're leveraging, and also the summation of power. Those are some things. So this is a block definition diagram. And then we're relating this to a constraint block that's trying to help us to be exploring power consumption. I'm not going to go through this in detail at this point. We'll be coming back to this on Thursday, and also some of this will bleed into next week when we start to stitch all these system diagrams together to form an analysis understanding of our whole system. So that's one. Here is another one that's looking at power consumption. This is a little bit later in the chapter. This is looking at the mechanical power subsystem. So that's something that we can be starting to be playing out a little bit more. Yeah, I think these may be the same. They're close. So I'm just going to skip over this. Just trying to give you a broad brush introduction at the moment. Another thing that Freudenthal talks about is a surveillance system. So this is now talking about the mount assembly. And so this is including a time-dependent constraint. And so how fast can it move from one position to another? That would be a temporal type of constraint that would be trying to think about. How fast can it go from one vector to another vector in space? Here is another one. This is another one that's trying to explore and think about time, representing time in a parametric diagram sense. And so the textbook talks about that. This is constraining an item flow. And so you can be thinking of, say, like you have some kind of fluid or flux or whatever, maybe constraining light. So this just gives us an idea. So you can have a polarizer. All of these would be things that you could be manipulating the performance, the flow of electromagnetic energy coming into the surveillance system, how well it's going to perform at day or night, stuff like that. You can also bind analysis elements together into a higher context. And so this is something that's a little bit later in the textbook. And so this is starting to get a little bit more advanced, and maybe what we're going to try with our first or second parametric diagram, but these are some things I at least wanted to give you a sense, and I augmented these charts with those few things there. So parametric diagrams, they capture the analysis as a network of equations. It helps ensure consistency between the system design and design model and multiple engineering analysis models. It helps to manage technical performance measures. The constraint blocks, it defines parameters and constraint expressions. It's represented on a block definition diagram. So I showed that earlier, and then made a few comments about how it may or may not work with our version of visual paradigms. The constraint properties, it's a usage of a constraint blocks and is represented on a parametric diagram. Okay, so that's a short, visually centric way of introducing a parametric diagram. I'll just show you a single chart here. And it seems like it bumps me out of sharing my screen, so I'm just going to show you this, and I'll dwell on this a little bit more on Thursday and the next couple of weeks. And so this is where, well, let me just show you the context of this. This is something that is a little bit dated, and I modified and put together a couple sources here. And this was a modeling and simulation of a CubeSat mission. And so this was looking at a specific mission, and I'm not going to get into those details at the moment. But let me see if I can go back to that chart here. And so here we could be having a number of different scenarios that you could be starting to play out. And so how is it going to perform under these scenarios with these kind of constraints? You're trying to figure out what you're going to put on your CubeSat, what you're not going to put on your CubeSat. You can think of like a CubeSat, a 1U CubeSat, it's a 10-centimeter cube. There's not a whole lot of real estate there. And so you want to try and think what best to put where. And so that's what I'm trying to be showing with that. All right, I'm going to go to our Freudenthal textbook next. I did give you a heads up on some of these diagrams, so I won't focus on that. And then I'll just read a little bit from this introduction, and then I'll go over to visual paradigms and start to show you some of the things there. So in this chapter, in chapter 8, modeling constraints with parametrics, it describes how to model constraints on the performance and physical properties of systems and their environments in SysML. This allows SysML models to support a wide array of engineering analysis and simulations. So analysis, simulations, those are the things that we're trying to accomplish with these. So a typical design effort includes a need to perform many different types of engineering analysis, such as trait studies, sensitivity analysis, design optimization. Some of those terms, if not all of them, should sound familiar with the things that we've been covering so far in our course. It may include the analysis of performance, reliability, cost, and physical properties of the system under consideration. SysML supports this type of analysis through the use of parametric models. Parametric model constrain the properties of a system, which then can be evaluated by an appropriate analysis tool. And we saw an example of what that might be. So you set up things, and you may or may not have a direct connection between those tools to do some of those performance. So that's just a little bit of a context I wanted to give before I just jump into some more in-depth things here. So here is in visual paradigms, something that a former student started to create, and I've modified it some, and I'll be trying to show you this and some other things to maybe give you an idea of how this might actually. Okay. Try to make it a little bit bigger. Okay, so here are constraints properties that you can do within the visual paradigms, the way things are set up in visual paradigms. And so that's what we see here. And what it does, it shows an annotation. These are constraints in the attitude control system. So this is related to attitude control. And so we can see that you're trying to measure the attitude. And so there's a lot of electronics that need to be done. And so we could flesh out more of those details. We can do an estimate of an angular rotation. So there's different things that are part of an attitude control system. You can have gyros, you can have thrusters. All of those are things that are part of what you could be thinking about. And so here, this was put in a folder or this package of orbit determination, and then you have orbit maintenance, and you can see that you measure the attitude, and then you have a certain delta V. Delta V is a term that's used with satellites. It's like you expel a little bit of gas, and in space, it's not like you're on the ground, you just have to push the accelerator pedal. You have to create that movement by losing something. And so you're ejecting some gas, compressed gas, and it's going to help you to move in a direction opposite to the direction in which that delta V was being applied. And so here we can have like a cold gas container. So you can be thinking about, I don't know if any of you guys are into biking, but some really high-end bikers, instead of like having a bicycle pump, they'll have like this little container of really high pressurized air in this little chamber. And so you actually can stick it onto your tire, and it's going to transfer air from that little container to your tire and inflate that tire. And so it's a lot smaller. And so they're trying to conserve weight and not have anything more on their bike than they need to. That would be an example of what they might be trying to do. It might give you an idea what like this cold gas storage is like for a satellite. Okay, I'm just going to flash this one up. I'm not going to talk about it. So there's two parts of this. Zoom in a little bit more if I can. Okay, so over here, this is just an image from Cameo Systems Modeler. And this was me trying to mimic that in visual paradigms to help make a comparison. This is dealing with orbit analysis. And so in the previous parametric diagram, I was showing you something related to attitude control. This would be related, but this is like, say your orbit is getting too low, like every once in a while, the International Space Station has to boost its orbit because it's getting a little bit of atmospheric drag where it's at. This is where this was trying to do, or maybe I'm trying to go from a low Earth orbit to a high Earth orbit. These would be the things of all of the things that would have to be thought about. These are some of the Keplerian orbital parameters. I'm not going to get into details of what that means, but there's different ways of how you can express an orbit. And so this is some of the things that would go in and out of what you're actually going to be doing to perform that change. So if you're going to squirt out gas, what direction and how much? If I wanted to orbit raise this a kilometer, that would be an example of what you would be doing. And so this type of analysis would be helpful for that. Any questions on that? I know that gets a little bit technical. This is one of the reasons why I kept the parametric diagram until last, because it can be a little bit more involved. But if you can be thinking about something that's maybe first of all, maybe by now, if you want to email me, that's fine. Think about what you might want to be doing an analysis in your design. And let's see if we can start to capture that in a visual paradigms parametric diagram. Okay, so you can also review this lecture and get a chance to be seeing some of the samples that I've been sharing during class. And we'll try and have it be a little bit more hands-on on Thursday. Any questions? Okay, I'll just do one last. This is now moving over to the Cameo Systems Modeler, the way I like to call it. And this is just going to be a few more just quickly showing you things, but this is now in a different tool. So they are both using the same SysML standards, but this just gives you an example. This is looking at an analysis context. You remember that we were saying that there are some contexts that you can be thinking about. I showed you this image, and this would be like an analysis context. You can have like trying to display an equation. So you're trying to be thinking about it from a slightly different perspective. That's something that would be there. This is, you remember I showed you that image that was in visual paradigms. This one, this is what it looks like in the source, just to give you an idea. And here is just another one. So these are all analysis context, but I'm going to be looking over some other examples that may be helpful to illustrate and make sure that you get a better sense of what a parametric diagram is all about. Okay. All right. Well, I think that's a good breaking point for now. And any other comments or questions? Okay. So I hope you guys have a good rest of your day, and I'll look forward to seeing you on Thursday.